perfect. So welcome everyone to another session of the data learning seminars. Today we have Julio Hurtado, who completed his PhD at Universidad Católica de Chile, and now he's currently a research associate at the University of Pisa in Italy. So Julio, I'll leave the audience with you and go ahead, please. Thank you for doing this.
Thanks for the presentation, and first, thanks for inviting me here. I mean, it's a really great opportunity to be presenting this kind of work. This work is mainly done here by the members of the University of Pisa, but also is by members of the National Center of Artificial Intelligence in Chile, CENIA. So let's begin with the presentation. If you have any question, or if I'm talking too fast, or sometimes my microphone make tricky situations, please let me know. Also interrupt me for any questions. So we can make this more like a dynamic presentation. So let's start. Today I'm going to talk about continual learning, specifically about this, what is a storage policy, and how can we select and the best different approaches for selecting the storage policy in different kind of scenarios. But first, I want to first introduce and motivate this idea of deep learning. I know that you guys work with deep learning, machine learning in general, so you know that how deep learning works. But I like to start this by motivating this idea of how I see deep learning, to introduce the idea of continual learning, and to the end you will see more like the whole idea of the situation introduced in this way. So let's start. How does deep learning work? So normally what we done in deep learning, especially, is that we have this big mountain of data, and give it to a model. And basically we say, okay, here, take these images of cartoonish animals, cartoonish cats, cartoonish dogs, and say, okay, this is a cat, this is a dog, this is a cat, this is not a cat, and go on and go on. With this amount of information, the model is able to correctly classify what is a cat in this cartoonish situation, this synthetic image situation. However, by assuming this, we are assuming that the distribution of the training set is going to be similar to the distribution that we're going to face in inference or in deployment. Because we're training the model in a way that is only focused on only generalized in this like limited way of the training set that we're facing. However, we know that this distribution shift happens. And what I am referring with this is, we know that in deployment, the model is not going to face cartoonish animals. It's going to face real cats, for example, real dogs, or sometimes we are going to we need to add new information about new animals. So this idea of distribution drift that we call is facing a different distribution in inference that we train the model. And this is not like very common to do it, but what happens is we face multiple distribution in a sequence of time. So we can face one, but we can also face an infinite set of distributions. So each time a new idea, a new concept arrives, we say, oh, we need to retrain, adapt the model in a way. And there are multiple like solutions or way to adapting the model. A very simple one that is not very useful, but it's the most simple one is, okay, let's assume that we are going to retrain the model or training from scratch or whatever, using all information from the current distribution. So if we have a sequence of distributions, here we have the training set, we have the different inference data. What we can do is, okay, let's focus on training on the current distribution. So most of the weights are going to face this, because how the optimization function and the loss function works is that it mainly focuses on the gradient in solving that particular task or distribution. So what is happening in the model is that the weights are going to focus in a way that is making an interference with what I have already trained in the model with the information that the current distribution have. So what is going to happen is that we're going to drastically lose the performance of these previous distributions. And this is the problem known as catastrophic forgetting. And it's very common in these kind of situations. So what's another possible solution for this problem of training multiple distribution at the like in a sequence? Another solution is, okay, let's assume that we have all the data available, like the past information, the past data, past distribution, current data, and so on. So one of the problems of this is that this increase the complexity of the training process. Because imagine we have a model that takes weeks to train, that is very common nowadays. So the problem is that each time we face a change in the distributions, we need to retrain the model with all the data, not all the data from the past, but adding new information as well. So the complexity increased. So this is kind of a big problem. Another possible problem is the availability of the data. Because of company policies or because we lost the data or privacy concerns, we don't always have information of previous distribution or previous data. So what we have, maybe we can have like a small percentage of it or something like that. And the third motivation of why this isn't a very good idea and is the one I prefer is this idea of humans can do it better. We as humans do train in a continual way of seeing things. As humans, we are like this kind of flexible learners, as I like to call. Because it mainly happens that as humans, we are learning new concepts every day, every hour of our day. And we make this quick adaptation in each of these concepts. For example, let's say we wake up and we go for a run. We are learning continuously to improve our running to the running itself. And what happens if we face a problem or we face a friend and we say hello? We quickly adapt to these new situations without having to retrain again and again to facing these new scenarios. And more importantly is that we avoid forgetting in all this process. Sure, we forget a few things, but normally we don't forget about important things, about this general idea of the things that we know. That is actually happening in deep learning models. So the whole area that focus on study this problem is known as continual learning. And it's basically trying to solve this idea of training in a possible infinite sequence of a stream of data or task. And the goal is similar as humans, as these flexible learners. We first want to extend the previous knowledge. So we don't want to stay with the knowledge that we have and try to adapt or reuse that information. We need to add new information from what we already know to solve the current task or the future task as well. We also want to try to reuse the information that we already know in our model. And most important is that we want to avoid or mitigate this forgetting. So this idea of continual learning can be not solved, but mitigated in different with different solutions. There are mainly three different approaches that we can use. The first ones are replay methods that I'm going to speak about in a little bit. And the second one is regularization-based methods that mainly focus on trying to minimize the modification of important weights in the for previous task. The definition of important is very specific for each of the methods, but that's the main difference. And we want to regularize this to minimize this idea of modification. And parameter isolation is this idea of each task, each distribution is going to focus on particular part or sub-part of the model. So we can have fixed or dynamics architectures. So let's focus on replay methods that are the ones that are more are having the best results and state-of-the-art in current approaches and scenarios. So let me. So about this. Okay. So this replay-based approaches basically is, as the name mentioned, is using this idea of repeating the information that we previously seen during each training process. So after or during we are training the current task, we save part of the information using a storage policy in a memory or a buffer. And when we train the new distribution, with the new data, we use the information of the current data plus the information of the buffer to train the model. So we constantly repeat information. However, this storage policy is very important because it decides which elements are going to be saved in our memory so it can be repeated. So this kind of idea of which information we need to save in this memory are very relevant to the idea of this replay-based method. Because we need elements that are going to be representing the whole distribution of the task inside this buffer. So how can we decide which elements are more useful to be saved in the memory? Well, there has been some works that propose different approaches. We can select those with bigger loss, those elements that have lower loss, or those elements that are closer to kind of a mean vector or of a feature vector of the class. So we can greatly represent each of the classes. We can populate the memory with a random sampling, or we can make a quota using a task or class balance between each of the classes or class that we have. So many different possible solutions. However, there has been a few works that shows that it doesn't really matter a lot, because in most of the case, random is a very good approximation. But we can think like intuitively that there is why random works so well. I mean, if we choose like bad luck or something like that, most of the data are outliers, that those elements are not representative of the current task. So why selecting random is performing so well in different scenarios? So we think about this problem, and we arrive to this solution that is proposed in this paper here, populating memory in continual learning with consistency-aware sampling. And we think, and most of this is like kind of a spoiler, because this is like kind of the conclusion, but we found that we need two attributes for a memory to be reliable. The first one is fast recovery or a fast adaptation, because we know that when we start learning a new task, the model is going to focus on that task. I mean, the optimization function is made in that way, because most of the loss is going to focus on elements that we haven't seen yet, those elements that we don't know yet. So most of the gradients is going to focus on those elements as well. So we're going to lose performance at the beginning of the first iteration of our training process, of our training, our new task. However, we want the elements of the memories to say, okay, we're losing performance. What can we do? And we can rapidly or fast recover this performance that we just previously had. So we need these elements to be representative of that particular task. And thus, it's like a fast recovery adaptation. And a second attribute is this diversity inside of the same class that I call. And it's the idea of, okay, we need diversity of all the classes. I mean, all the classes has to be representative represented in the memory. However, we also need diversity inside the class. Inside a class can have many concepts. Let's focus on the scenario that I proposed at the beginning, this idea of the cats. So we can have synthetic cats, we can have cats in a tree, we can have cats in the real world, cats in the house. So each of these cats represent a concept of the same class, the concept of the class cats. So each of these concept inside the class must be represented if they are not outliers. If they are outliers, we don't want to set them in the memory. So we need to focus on what is relevant, but also what is important for the current class. So let's focus on the first attribute. If we focus on the first attribute, we can say, okay, there has been some work in curriculum learning that's focused on this idea that easy to learn elements or samples have the ability to are learned quicker in the learning process. So we start by learning this easy to learn, so the model can rapidly adapt to this new situation, and then we're like slowly increasing the amount of difficulty in the examples. And one way of identifying these easy to learn samples is this idea of consistency score. And the C-score or consistency score is how learnable each example it is within the same dataset. And one of the way of calculate to measure this consistency score is by training a big amount of data set, of model with the same data set. So the C-score is going to tell us the proportion of correctly classifying an element within a certain threshold of iterations. So if a sample is very learnable, we know that that example is learned at the beginning of the training process. So it's an easy to learn example. So with this idea in mind, we propose two storage policy. The first one is a high consistency. So we select only for example, this is the distribution of how the C-score compared in a data set. By selecting the high consistency element, the easy to learn elements, we say, okay, let's focus on with a memory size of 100, let's focus only on the top 100 elements. On the other hand, if we select the low consistency element, we select only the lowest 100 elements. So we expect that by using this selection of elements, we can learn faster and recover faster when we lose this performance when using the continual learning scenarios. And this kind of happens when, for example, here we have reservoir sampling storage policy that is kind of a random that simulate the distribution of the training set. A class balance, task balance, MF is mean features, this idea of the elements that are very near for the mean vector of the class, and our two proposals, lows and high C. And we test this in Cypher 100 split in 10 tasks, meaning that each task is going to have 10 classes. And with a memory size of 500, 1,000, 500, but using a different architecture, a RESTnet in the last case. So what we see here is, okay, our consistency sampling, like high consistency, is indeed better when we have fewer epochs. We achieve a pretty big margin compared with the state of the art, this MF, by 3–4% of accuracy. So, okay, it's working in some way. However, when we increase the amount of epochs, it's very similar to what is done already. So why does our methods work well when we train with few epochs? Is because this fast adaptation thing. And we make like a double click in these results. And we test this also in Cypher 10. with different amount of memory size. In the case of figure A and figure B, we use only one epoch to prove the point that I am going to give you right now. So by increasing the amount of memory size using only one epoch and selecting only the high consistency element, we can indeed improve the accuracy, something that doesn't happen in this mean feature storage policy. We can hypothesize many things, but mainly focus on the idea of what we are doing with high consistency elements is removing the possibility of having outliers. Instead, with mean features, you still have this possibility, this probability. As indeed, what we expect is that because we are selecting the high consistency elements, we decrease the forgetting in a big margin. And that's what's indeed happening. In figure B, we can see that by selecting high consistency element, we decrease the forgetting by increasing the memory size. However, and this is the but in our results, is that if we increase the amount of epochs and still with a memory size of 2000, we can see that the mean features like highly increase the accuracy, like 20% of accuracy increase. However, high consistency element, it doesn't increase that much, like a 5% of accuracy. And this is very, very interesting, and it's mainly focused on the idea of diversity. Because if we only select those elements that are very consistency, because our very consistency, it's mainly focused on a limited amount of concept inside the same class. So when we can train for more epoch, we can't train for more concept because we don't have this idea of more concept inside the memory. Instead, mean features, it have this diversity in it. So what we do in our proposal is, okay, let's add this idea of diversity by proposing this consistency-aware sampling. So imagine that we have a memory of size 3, for example. If we select the top consistency element, we're going to select these 3 elements that we have in the right. If we select the lowest consistency, the 3 elements are in the left. But if we set a threshold of the consistency that we want or need in our pool of data, we say, okay, let's set a threshold of 0.7. So we have all the elements of the current distribution with a consistency score higher than 0.7, then can be sampled from our storage policy. So we select 3 samples from this pool of elements that are higher than a certain threshold. The idea of this is that we want to remove the possibility of outliers, because we know that low consistency elements are going to be behaving like poorly, very poorly. And this indeed happens in different like situations and scenarios. For example, Cipher 10, Cipher 100, Cipher 100 we used in a ResNet. We see that CAWS improve the results or have very similar results than mean features, in the case when mean features have like better results than high consistency. And in the case of when high consistency have better results, we indeed see that CAWS, that is the green line on the top, is that CAWS have better results than high consistency. Even if we increase the amount of epochs, if we increase the amount of memory size, if we decrease the amount of memory size. So in many different scenarios that we test this, CAWS indeed have better results. However, we have a new threshold, so a new hyperparameter. And hyperparameter is not like good things in the area because we have to tune it. But this idea of the thresholds can be very related for the distribution of the Z-score that we have. So let's focus on this graph. This graph shows the accuracy when we set different thresholds and different memory size for Cipher 10 and Cipher 100. What we see here is that the accuracy in Cipher 10 is very like uniform. It doesn't change much with the threshold that we set. Instead, in Cypher 100, we see like this inverse U of idea. So we have the best result using a threshold 0.6 or 0.7. And it's very similar with the idea of this Z-score distribution. If we plot the distribution of the Z-score for Cypher 10 and Cypher 100, we see that Cypher 10 is very skewed, and most of the elements are in the right side of the distribution. So by setting a threshold of 0.6, for example, most of the elements are going to be present in that pool. So the difference of accuracy doesn't going to change a lot. However, in Cypher 100, we see that the distribution is more uniform. So changing the threshold can change a lot the accuracy that we are expecting. So, yeah. However, I'm going to shoot me in my own leg. I don't know if that's a saying there in English, but there is a big limitation in CAWS. And is that we need this pre-calculated Z-score. The idea of Z-score, as I mentioned before, is that we need to train multiple models and select the proportion of elements, or sorry, the proportion of correctly classifying an element inside a certain threshold of iteration. So we know how easy or hard it is to train that particular element. But we need the whole data set to do that. So the idea, and it's very costly, of course, we need to train many, many models. So the idea of using CAWS in continual learning is not feasible, it's not possible, because we need to have this pre-calculated Z-score. So for that, we propose a new way of calculating the Z-score by using this kind of proxies. So what do we do is propose this idea of selecting the feature vector of each of the elements of the current task. So we extract the feature vector and create a space of elements inside this spectrum of all the elements in the current task. And what we do is, okay, how can we select the most easy to learn examples? How can we create this proxy? So we pass the model, extract the features, and we say, okay, what's the meaning of being consistency? Sorry, of being consistency. And what is make this idea of concepts and how learnable a concept is inside the class is the idea of the neighborhood that we have. If the neighborhood of a particular sample is full of elements of the same class, it means that that particular sample should be consistency, because it's far away from other classes and is very near to current element of the class. So what we're seeing here is, okay, let's focus on this idea to create these proxies. And for example, in these examples, we see for this blue dot here, we say, okay, half of the elements are of the current class. So this element is half consistency. So the score is going to be 0.5. And we do this with all the elements of the current class. So we propose 3 proxies. The first one is, okay, let's use a pre-trained model. We use a ResNet 18 pre-trained in ImageNet. And we select and set this score with all the elements of the current sequence. This is not feasible for continual learning, but we set this as a threshold, as a baseline that we need to see if our proxies are actually working or not. As the second proxy, proxy 2, is we use the same pre-trained model, but using only elements of the current task. And the third proxy says, okay, let's assume that we don't have a pre-trained model. Like is a very niche data set, so we don't have pre-trained model, and we use the model of the current sequence in the continual learning sequence, and use the elements of the current task to select the score. And we can see here the results. What we can see is that in all cases, one of the proxies is going to be one of proxies 2 or 3 that are the ones that are feasible in continual learning are going to be better than mean fitters. So by using CAWS is going to be better in most of the cases than selecting with mean fitters. Using different amount of epochs, different amount of data set, different amount of benchmark, even different amount of memory size. What is very interesting is that in some cases, Cypher10 and TinyImageNet, one of the proxies have better results than using CAP using the original Z-scores. And this is kind of surprising for us, but we don't have like a complete and real answer for this question. But our hypothesis is that CAPS, Z-score, it's good to finding these really easy to learn the examples. However, it doesn't incorporate this idea of multiple concepts inside of the same class. And that's exactly what we do, and we're trying to do in CAPS. So for CAPS in particular, this idea of the proxies can be more useful than using the current Z-score, the Z-score score, the consistency score. So that's kind of one of the work that we have been doing in the few months now, however, there is not only that. There's a big limitation on not in continual learning per se, so this is kind of misleading, but in the idea of the benchmark that we are using in continual learning. So I present you this idea of, okay, in continual learning, we train this with multiple distributions, and each distribution has its own classes and have this idea of disjoint classes between the distributions. So, for example, in distribution 1, we train only with information about snow. Distribution 2 only about information about rocks, and distribution 3 only about information about trees. However, we know that this is not realistic. I mean, it's not realistic that in real world application, you don't see this like a strict task with only information about a particular class and so on. What we normally do in realistic scenarios is that we see applications where when a new task arrives, a new distribution arrives, it can have information about new classes, it can have same samples of previous classes, and it also can have information about previous classes, but it's also new. What is the meaning of this? I mean, if you know what a bottle is, and you imagine, okay, this is a bottle, probably what you are imagining is the idea of this plastic bottle that we normally use to buy, I don't know, water. However, if I told you, oh no, this is a bottle, this is also a bottle, and what we expect is that if you haven't seen that kind of item before, you add that information. Okay, I know now this is a bottle, and this is added to your knowledge about this all kind of items. So this idea of natural repetition is very common in these real world applications, and is not reflected in current continual learning benchmark. So what we propose here in this paper is mainly this idea of class incremental with repetition. And it's focused on this idea of the limitation of current benchmark that we have. So the first one is, let's focus on the benchmark that continual learning have right now. The first one is class incremental. Class incremental said this idea of each task has its own task. So that's this joint set of classes. So class 1, 2, and 3 only appears in task 1. Class 4, 5, and 6 only in task 2, and so on. This so this idea of not like this realistic way of saying things. The second common benchmark is this idea of incremental domain learning. That data can change, but it's the same classes. So in every task, we see the same classes, but with different data that can be changed. But is here the restriction that we need to see every class in each of the task. However, what we are proposing right now is this idea of repeating classes in a natural way, so with a probability. So we propose a scenario generator that can control many things, but the three important things, just to be wrapping up, the three important things is that we can control the length of the string, because we are not like restricted by the amount of classes that we have, because we can repeat all classes. We can have a string as long as we need, or we propose. The second important thing is that the probability of the first occurrence. So we don't set an exact moment when a new class is going to arrive. We set a probability of first occurrence. And the first one that is very relevant for the storage policy idea is this probability of repetition. So the probability of repetition say, okay, now we have a task a class that can be more common than others. And this idea is like, as an example, this idea is very realistic in a way of seeing the benchmark. I mean, it's common to see chairs, desks, but it's uncommon to see, I don't know, lions or any kind of wild animals in the city. So classes can be more common or uncommon. That is something that didn't happen in this classical continual learning benchmark. And if we focus only on this storage policy situation, is that because we now have these non-uniform distributions of classes, we don't want this, for example, this idea of class balance, where each class is repeated, because we expect that if some classes are naturally repeating in each of the tasks, or in most of the tasks, doesn't need to be appearing as much in the memory as other uncommon classes. So what we expect is that uncommon classes to be overrepresented in the memory or the buffer. So we propose this frequency-aware policy that we basically found the frequency of the classes during training, like in an online way, and set a quota that is inverse to this proportion of the frequency of each of the classes. So here we can see the ratio of uncommon classes using different storage policy. Using a class balance is simple. We see that each class has the same probability of appearing in each in the memory. Using reservoir sampling is overly represented the more common classes, with our proposal we overly represent these uncommon classes. And I don't want to mention much about the accuracy, but let's increase the accuracy of this scenario as well. So let's wrap up a little bit. So here we present different scenarios, different benchmarks, different situations, different memory size. And we see that the storage policy is indeed very important to be selected correctly. Not only because of we need to think about and tune this hyperparameter, but we can think about in better ways of selecting this storage policy in like a more intelligent way. For example, we propose using this memory composition or the distribution of our data set using the consistency that we have. We know that we can select elements now that are more consistency and that remove this possibility of outliers. And CAWS is the proposal there, With CAWS, we remove this possibility of outliers by overly representing and better representing each class in the memory by giving diversity and fast adaptation elements. On the other side, we present this scenario that is with this idea of joint classes, because we propose that these joint classes is not realistic. So what we propose here is this idea of a class incremental with a natural repetition of seeing things. And of course, this idea of new storage policy that can be very useful in this kind of scenarios. And with that, I would like to finish the presentation. Oh, something that I forgot about it. Most of these methods are implemented in a framework called Avalanche. Here, I don't know if any of you work on continual learning or are thinking about or of working on continual learning, but Avalanche is a framework that we have been promoting here in the University of Pisa. That is basically to start working with continual learning, because have many different ingredients in like separately very well. So if you are planning to start working on continual learning or you are using continual learning, please check Avalanche. It's a very useful framework based on PyTorch that can be related or useful in the future. And if you have any questions, please let me know. I can answer it here, or you can send me an email. I don't have any problem with that. So thanks for listening.
Thank you, Julio. That's a very interesting talk. So you have any questions for Julio, just you can type them in the chat and I can read them out loud for you, or just unmute yourself and you can ask yourself. Let me see if I have any. And in the meantime, I have a couple of questions. So mainly this work is about classification. Can this work be used for like a regression problem? Will that be too difficult to modify, or what are the challenges that you see applying it to a regression problem?
That's a very interesting question. I haven't seen works with regression in continual learning, but I believe that it's mainly apply the same ideas, because in continual learning you use this idea of regulating the weights or using this memory to regulate the forgetting of previous knowledge. And if you have a scenario of regression that you have this continually stream of tasks, it can be useful to use continual learning if you don't have access to all the previous data and all that.
I was thinking like in some kind of like forecasting scenario where you can, well, you have LSTMs that kind of forget what happened before or keep the information, but maybe, yeah, maybe like in a forecasting scenario, you can learn more data will come in, let's say like weather forecasting. You get new data all the time, but then you can choose which one to forget. So I think maybe it could be useful in that sense, but I don't know how difficult it will be to adapt to a different problem.
I don't believe it's going to be that difficult, because correct me if I'm wrong, I don't usually work with regression, but the main difference with regression and classification is just the last layer and the optimizer that you use and all that. And if you change those things, most of the method of continual learning can be applied to regression problem without any problem.
All right, cool. And so I just wrote down a couple of questions. It's no more. And in terms of scalability, for example, you show results with CIFAR10 and Tiny ImageNet. What happens if you choose like a different? How does it scale to a problem with a data set with a lot more classes?
Yeah, that's also a very good question, a very good point that many reviewers ask continually in many situations. But no, the answer is mainly the problem in continual learning is that you have to apply this idea of continually train.
Mhm.
And normally you train with multiple epochs for each task. So it's very costly retraining the whole data set, the whole sequence each time. And if you plus that, you have this big amount of data like ImageNet or something like that, the amount of time and compute that you need increase like in a big margin. So for example, if you can train Cypher 10 in an hour in a normal way without continual learning, you need 3, maybe 4 hours to do it in a continual way, because you have to split the data set, you need more epochs, more iterations, and that's more costly. So imagine that with a bigger data set, well, if you have the GPUs to do it, okay, let's do it. But we normally don't have the GPU to run that kind of experiment, unfortunately.
But the bottleneck will come from the number of classes or the number of samples that you have?
No, in a way of saying, if this can be done, yes, it can be done. If you have the computation power to do it, it doesn't have to be a problem to be the amount of classes or the amount of samples. Maybe can be the amount of samples if you divide the dataset in too many tasks.
Okay, yeah.
But other than that, I mean, it shouldn't be a problem of if you have the computer power of doing it.
Okay, yeah. And yeah, 2 more questions. I don't see any other. Yeah, I was gonna ask you about the generation of new scenarios. Can you go back to that slide?
Yes.
So then here, sorry, can you explain again what do you mean by scenario in this case? It's like, yeah.
Mm-hmm. So these are many dialects. Let me see if I can. Okay, yeah. With a scenario, we talk about this idea of the sequence that we train our model. So a scenario for me is the different tasks that we have, the amount of tasks, the classes per task that we have. And so this scenario generator is saying that we can create a sequence where we set some kind of hyperparameters that are the probability of the first occurrence, the probability of repeating a class, or the length that we have the stream. And with that, we create this scenario, and say, okay, first task is going to be represented by class 1, 2, and 3. Second task, and so on.
Oh, okay. I'm just thinking of like when the current thing I'm working with dynamical systems. So sometimes we have this like massive simulations that take a long time to produce. So there will be a lot of benefit to try to reproduce them and maybe generate new scenarios without having to simulate something again. So that's why I was interested in seeing what you guys do. Like just trying to like modify to the regression problem again. Yeah. And then yeah, the last question was about can you explain a bit more about Avalanche?
Yes, of course. So Avalanche start and is continuous, powered by Continual AI. Let's speak about a little about Continual AI. Continual AI is a group of many researchers that we have a Slack if anyone wants to join, that work on continual learning. Saying that, Avalanche worked with this problem of law of reproducing experiment in the continual learning community. There was some point that each of the works that was presented start with the idea of the new scenarios. So a new scenario is in a way, let's focus on different amount of tasks, different amount of classes, different amount, and so on. So Avalanche and some other frameworks start and were like initiated with this idea in mind. How can we improve the reproducing experiment in the continual learning community? And Avalanche is one of these like projects that start on that, and it's one of the frameworks that is more popular in the community, and have some or not some, not that many, have some methods already implemented. Some have most of the most common benchmark already implemented, and you can generate different scenarios and set different hyperparameters. So it's like very easy to start doing experiments without any like actual knowledge of continual learning.
Oh, okay. So kind of like a Hugging Face approach.
Yes.
Okay.
Not that oversight, but yeah, it's the idea of like trying to be a first step on this continual learning.
Okay, yeah, and it's a PyTorch, right?
Yeah, it's based on PyTorch, and we are working on, still working on it. I mean, it's a continual iteration of branches.
All right, cool. Yeah, I think that's it's 5 p.m. now, so we can leave the talk up to here. Thank you, Julio, for your very interesting talk, and yep, thank you everyone for attending the meeting today.
Well, thank you for having me here.
Yeah, no worries. Bye-bye.
See you. Bye.